Okay, good afternoon, everybody. This is our first attempt to have an SIAE webinar. We're going to talk about the future of aviation post-COVID-19. Okay. SIAE made a painful decision to cancel SATEC 2020 when DESCON went orange in February 2020. But the impact on aviation is far more severe. Thousands of aircraft were grounded, and many more aviation workers were laid off as travel restriction continues. The economic impact is further multiplied with worldwide shutdowns to travel and hospitality businesses. Pandemics, like revolutions, tend to shift power from one section of the community to another. After the Black Plague killed 60% of Europe's population, the production system crumbled, which diminished the powers of the feudal lords. More importantly, focus of learning moved away from heavens to earth, resulting in the Renaissance, which led to the scientific and industrial revolutions in Europe. How has COVID-19 changed our life fundamentally? Online shopping and e-learning are two clear beneficiaries, while the hospitality industry suffered gravely. Aviation is an important driver of the hospitality industry. What changes can we expect to see in the traveling pattern of people? How will these changes affect design of aircraft, operations of airlines, and airport? This afternoon, we have brought you two very experienced people to look far into the future. Dr. Cyrille Schwob, Head of Technology, Asia Pacific at Airbus, has more than 10 years leading technology with Airbus, both in Singapore, Malaysia, and today he's head of Asia Pacific in Airbus. We have Professor James Wang. Oh, he has a long history of innovation. I won't read all, but I just want to read one sentence which probably tells everything. Wired magazine, they named Professor Wang the Steve Jobs of rotorcraft for inventing the world's first all-electric vertical takeoff and landing aircraft in 1918. Okay. Professor James will look past 10 years, 20 years ahead of how VTOL is going to change our travel pattern. So without much ado, I will now invite Dr. Cyrille Schwob to present his story. Cyrille?
Hello.
Hello. Okay, go ahead.
Hi. Thank you for the kind introduction. I hope you all can see my slides. Is it working?
Sure. Good. Go ahead.
Yes?
Yes,
okay.
looking good.
So like you, I've been, so Prof Lim, thank you very much for inviting me for this talk. I've been discussing a bit with you what would be the ideal topic to discuss in this particular time and what would be the most optimistic and forward-thinking topic. And of course, this comes exactly at the time where Airbus has announced a very ambitious program, somehow to save also aviation in the longer term, right? This is our idea to use hydrogen as propulsion for aircraft. I will start the talk by this beautiful picture, right? It's making a lot of us nostalgic. This is plane routes in Europe at the time when we could fly as we want. And this has, for myself as a French guy in Singapore, right? I'm missing my parents in France. I'm missing my friends in Malaysia, in Thailand. This difficult time is showing us exactly how important aviation has become for our societies, right? It's good for our economies, of course, but it's also good for every single of us of our personal life. And we all strive to go back to this world where we can all meet new culture, see our families and our friends. Even if we can go back to COVID, when you see this kind of map and the type of contacts that you can do through aviation, this is an exponential thing, right? So if you want to make it sustainable beyond COVID, but in 50 years from now, in 100 years from now, you need to start to think, can you hear me? I get some message that it's unstable. Is it okay?
Yes, sure. Cyrille, go ahead.
Let's assume, is it okay? It's okay, I continue.
Yeah,
If we want to make sure this is sustainable, we need to think of what kind of challenges are coming with it. And one of the challenges, of course, is how can we produce that many aircraft? And this is a key concern for Airbus, right? This is our core business. And the second one is how can we make it sustainable so that it has a limited impact on the environment and so that it can support the sustainable growth of society. So this question is not a new question, and not only Airbus, but the aviation as a whole has been setting up has been thinking about it. And we have set up some very ambitious targets back a few years back already. And the target has been year on year 1.5% improvement in fuel efficiency. And this over the past 50 years, the plane as of today, they are consuming a lot less fuel than they used before, less than 50% than before. We want to move towards carbon neutral growth from 2020. And this is an objective that still stands today as of today. And then we want to have a target, at least 50% CO2 emission reduction for aviation in 2050 compared to 2005 baseline. And these are objectives that are at the industry level, and they are driven a bit by ICAO. And I will show you in the next slide a bit. There are four avenues for every single aviation companies to move towards this objective, and 4 basket of measures if you want. The first one, what I wrote here in the lower hand corner, market-based measure. And this refers basically to, you probably have heard of the CORSIA scheme, so the carbon offsetting reduction for international aviation scheme. This is, for the moment, it's a voluntary scheme where basically when you consume CO2, you need to offset it. So it's a market-based mechanism to make sure that you have an incentive to use less CO2. This is already being rolled out in a voluntary phase until 2025 or in this area. And then from 2025, it will become mandatory for every single country that are producing more than 2% of aviation traffic to onboard this kind of phenomenon. The second basket of measure is operations. And basically, if you operate your plane better, you're going to consume less fuel. If you consume less fuel, then you produce less CO2. I'm going to give a very simple example, a funny one. If you fly with a clean airplane, meaning that you have been cleaning the exterior of the fuselage, you're going to consume 1% less fuel on long hauls than if you don't clean your aircraft before. So this is the type of operation measures that you need to take into account. The third basket of measure is what we call infrastructure. And the most impactful one is to work on traffic management to make sure that you are taking the most direct route between from A to B, that you're not circling around the airport too long, that you're optimizing the path of the different airplanes. And the last one, I keep the best for the last, of course, because I am myself a technologist, right? This is new technology. So in this basket, we have creating the best plane possible. And you have the image in the background, the A350 is still the most fuel efficient plane that we have on the market at the moment, made out of composite and so on. So I will give more details later. And I include in this basket also whatever replacement fuel, alternative fuel that we can come up to power the aircraft. This is new technology. So developing technology, this is nothing new for Airbus, right? Airbus is a 50-year-old company, but you can even go further, right? Because it's built on pre-existing companies that aggregated together to go on the Airbus journey. But from the 1970s to the 2020s as of today, I've just put some of the most most known technology bricks that we have pushed slowly but surely on board our aircraft. And you will see here at least two different types of categories that are related to sustainable. The first one will be introduction of new materials, and in particular composite material in the structure of the airplane to make it lighter and lighter and even lighter. And as of today, the A350 in mass, there is 50% of the structure that is made of composite. So it's lighter, so it's more, you need less fuel to propulse it, so it's more fuel efficient. And then we have been doing this step by step, right? This is aerospace, you need to make it safe. So we started by replacing some secondary structure made of composite, and then we introduced a bit of primary structure on the A320, and then slowly but surely we created for the 340 the composite keel beam, which is a major primary structure, and then for the A380 the introduction of the in the 2000s the part where you put the wings. I forget the name, the center wing box. And then all the way to 350, most of the structure, important structure, are made of composite to make it lighter. In parallel, you have a second type of technologies that are very useful for fuel efficiency, and this is what we call the more electrical aircraft. So more and more, instead of having different type of power system on the aircraft to power the flight control system, for example, instead of having hydraulic, electric, thermo, mechanical type of power systems to action some system on the aircraft, we are slowly but surely grouping everything under an electrical system. And this is what you see here with electrical signaling for secondary control, fly-by-wire, all the way to activated thrust reverser, where you need a lot of power there. And we have been working on this, and again, introducing slowly but surely more electrical power on board of the aircraft. And we are at a point today where on the S350, you have 2 megawatt electricity that is generated on board. So this is basically the kind of electricity you need for a small town. So this is already massive amount. Now, what I'm describing here is something that we have ourselves. We were in the driving seat, if you want. We develop technology. We make sure that it goes on the plane slowly but surely, step by step. The world is accelerating. Everybody is talking about digital. We are more and more connected. And what was true before is less and less true. We are not always in the driving seat anymore. And sometimes we need to look outside of the aerospace ecosystem to understand where are the new promising technology. And for example, if you look at evolution of the electrical car stock, this is exponential, right? And so this tells us that the technology at some point it will reach a level of maturity and a cost per, for the energy stored that is going to be useful for aerospace. Similarly, and maybe more even important for the topic of today, I'm talking about hydrogen, the growth of renewable energy. It started from something that was barely noticeable 10, 20 years ago, and now this is exponential. I guess the growth of renewable electricity is an exponential thing, and this is actually key when you're trying to do zero emission type of aircraft, because if you're creating electricity somewhere, you're creating energy. If you want to create energy, there is no magic happening here. You need to input at least the same amount of energy, right? And if you input an energy that is not from renewable sources, you're just creating CO2 upstream, and you didn't solve any problem, right? So this is very key in trying to achieve a zero emission, is to make sure that if we use hydrogen, if we use electricity, it's been generated by renewable energy. So looking at this, we tried to jump on the wagon of electricity and more electrical aircraft and powered aircraft. And we did a demonstration almost 10 years ago, so seven years ago. We actually made a very powerful statement by crossing the channel again, but this time with an fully electrically powered aircraft. So this is what we call the EFAN. It crossed the channel solely powered by electrical power. The purpose was to show that it was possible to get something in the air just with electrical power. So this is a great success. It's a reenactment of an historical milestone, but there is still a very long way from a two-seater, like you can see on this image, all the way to an S320 with 100 plus passenger on board. So we created a roadmap to try to leverage this. How can we push as far as possible electrical powered system? And we have done a variety of different type of system, and some of them will be very much in line with the domain of expertise of Professor Wang, I guess, because we have a bit of personal air vehicle, rotorcraft type of vehicle. We have demonstrator all the way to this city Airbus here, is 2 megawatt engines that are propulsing this in the air. It's a pretty big bird, right? It's doable, but it's still very long from a 200-seater. In parallel, and I will go to hydrogen now, there is some limitation to batteries. We've always been investigating what if for alternative fuel like hydrogen, and Airbus ourselves, you know, we do airplane, but we also do some rockets, right? We are sending rockets in the space, and you know that these are fueled by liquid hydrogen. So we have a bit of experience in this field also, how to manage hydrogen. And 20 years ago, there was already some studies in Airbus. What if we could power aircraft by hydrogen? There is some questions, and I'm going to show a bit this to you. So to the heart of the presentation now, introducing this concept that we are trying to push now, hydrogen-powered aircraft. We deem this program ZEROe and zero emission for zero emission. And we move to hydrogen is a natural choice somehow, because if you want to achieve zero emission, if you burn hydrogen, you're creating, basically you're creating water, right? And this is something that we can deal with. There is always a problem of where you're creating this water. Are you going to create more contrails? For example, if you produce this somehow too high in the atmosphere. So there is some trade-offs to be investigated, but it's a major step. It's a disruptive step compared to CO2 emission. The cost of producing hydrogen is going to decline also a lot, and I'm talking about green hydrogen, right? And as of today, it's way more expensive to face the reality, right? To produce hydrogen, 1 kilogram of hydrogen is going to be 4 or 5 times more expensive than the equivalent of kerosene, meaning that economically, we still have some progress to do on the ecosystem itself of producing hydrogen. And then hydrogen itself is a very energy dense gas fuel. So it means that if you want to do a transatlantic flight from Paris to New York, you can reduce the weight of fuel that you're going to take, right? From 40 tons of fuel, you just need 10 tons of fuel, for example. So this is on the plus side. On the minus side, it's more energy dense, but the volume is going to be way higher actually. So it means that it will have an impact on the design of the plane itself. You cannot just put hydrogen in the wing anymore, so you will have to think again on the design of the aircraft. I will come to this later. Then how to use hydrogen. This is not where the main blocker is. Basically, we know it's not like we never got a plane to fly on hydrogen, right? This has happened in the past. We are putting rockets in the space with hydrogen. We know how to do that. You can combust hydrogen directly in the motor. This is the first type of technology. And if any, this has only advantages because the combustion is going to be at a lower temperature. So it means that the engine will be more durable. There will be less maintenance. So this only advantages. It's really doable, right? There is 2 other types of technologies that we can consider. One, which is not really mature yet, these are the fuel cells. But there is, again, this is not driven by aerospace. There is this, the ecosystem of fuel cells for cars, for example, is developing very fast. And you could imagine at the very least that in 10 years from now, a 2 megawatt hydrogen fuel cell would be available to replace the APU or to support the starting of the engine or something like that. And then the third point, back to alternative fuels. You can actually use hydrogen the same way it's used as of today. You know, there is already hydrogen production in the world, and it's more for the petrochemical industry to produce petrochemicals, right? But you can use hydrogen, combine it with CO2, and create a fuel that can be burned in existing planes as we are flying them today. So this could be a bridging between today, using normal fuel, all the way to 2050, where the fleet will be the worldwide fleet of airplane could be replaced by a hydrogen-powered airplane. Okay, so and now the vision of Airbus. It's important to say here now that these are concept planes. This is just to help focus the 10,000 engineers that you can find in Airbus and in the ecosystem and the supply chain, to help these people have something in mind to know what what we have in mind. And basically, what you can see here is what Airbus wants to do is put the hydrogen tank somewhere in the fuselage, right? I was mentioning earlier that hydrogen is very massive. You need to store it in something that is more or less circular tanks. So it means it's not going to be in the wings anymore. So you need to put it. The easiest part is to put it in the fuselage, and you will put it here. So this will have some consequences in where is the center of gravity of the plane, where do you put the wings. But basically, you see you have something in our three concepts. Hydrogen would be here, passengers would be here, and three different type of airplane. One replacing the A320, so 200 type of passenger, 2,000 nautic miles taking you from Singapore all the way to Shanghai or to Perth, for example, and propulsion by burning hydrogen with a bit of, so we put hydrogen, hybrid hydrogen, right? A turbine burning hydrogen and maybe an electrical motor to help the torque further. The second concept is turboprop for a smaller number of passengers and a smaller nautical range, so for regional type of purposes, 100 passengers. And the third one, which is more, it looks more exciting on the picture, right? So this is an aspiration to start to think out of the box also. If you don't have a fuselage anymore, then you're a bit more free on where do you put the hydrogen tanks, where do you put the people, where do you put the power system, and so and so. So there is more in this one. Okay. All of this looks very nice, but there is some challenges, right? And the first one is technology compatibility. So basically, how can we produce hydrogen at the correct price and bring so you need to, the plane will be bigger, right? So what kind of material you're going to use to build the plane coming with it. Then you will have, can we have the ecosystem for distribution of the hydrogen? What kind of infrastructure can be used? Can we reuse the current infrastructure? What are the regulations that needs to be put in place? And what would be the acceptance in the public also? Because, you know, there is always this association of hydrogen with dangerous, which of course it is not, right? If something goes on a plane, it will be completely safe. We use always the same approach as what I was showing in the first slide. We introduce technology step by step, and there will be as many demonstrations and as long as possible testing the material and the different logistic configuration to make sure that everything is safe. In parallel, I was mentioning sustainable aviation fuel. This is not something that that is dead now, right? It's not because we talk hydrogen that there is no future for sustainable aviation fuel. In particular, in bridging the time gap between now, today, and in 20 years from now, when there will be wider replacement of the existing fleet. So there is still some space for sustainable fuel, and we are still very active in certifying different pathways of producing fuel to make sure that there are drop-in fuel that you can put in the airplane, and we can go up to 50% of blend, usually between kerosene and alternative fuel. And if when you produce the alternative fuel, you're actually capturing CO2, right? Then you can achieve some very high CO2 reduction targets, up to 85% CO2 reduction. And then very quickly, our path to creating this aircraft. I was saying the technology, we are going to explore them in the next 2 to 5 years. Investigating the material, the configuration, creating prototypes and demonstrators so that we can collect enough information to go all the way through the certification process, right? We need to look at all the aspects, not only the propulsion by hydrogen, but what is the impact on the climate, what kind of other emissions are going to be done, how we can optimize, for example, the combustion so that not only we don't produce CO2, but we produce very little amount of NOx. How we reduce the noise, how we integrate with existing infrastructure. What is the market also? Because, you know, Airbus, we are producing aircraft and products for our customer. So our customer will be able to take on the aircraft only if the price of hydrogen has reduced, or if the price of hydrogen has not reduced, what kind of incentives are in place, what is the market for it, the customer acceptance, and so and so. So these are all hypotheses or questions that we need to answer in the next 5 years. And to do this, again, this is the same message I was saying at the beginning. This is not something where we are in the driving seat and we decide everything. We need to collaborate with all the stakeholders and the wider ecosystem of the hydrogen producer, of the airport, of the infrastructure, of the regulations for hydrogen transport and storage. I just finished with a few dates. Project launch. So I put here 2018 because actually hydrogen has always been in our mind as one of the alternatives. We waited some confirmation to launch it officially this year. So this is what we did, pre-program launch. The key dates are by 2025, we need to have product selection where the concepts, the technologies, they are selected and we know how we want to apply them. And we are sure that it's going to meet the market and that our customers are going to be happy with it. And then if you launch something in 2025, you can expect 5 to 10 years for the program development to have entry into service of these beautiful airplanes with our customer. These dates they've been retro-engineered, if you want, so that we can achieve 2050. If you want to have 50% reduction of CO2, you need to have enough time to renew the fleet, right? You need to allow at least 10 years for the airline to renew from fuel kerosene consuming type of airplane to renew this fleet by the hydrogen plane. So this is our view, our vision for a zero emission airplane. And I will stop there. I hope I didn't take too much time.
Well, thanks, Cyrille, for a very interesting look into the future. We have a question time for you. 5 minutes, 2 minutes. I think we are a bit tight on the schedule.
Yeah.
Right.
Let's go.
Yeah, because our speakers are very busy and they have to move on to other seminars. So I'll move on. I'll move on to the next speakers. Is that all right?
Yeah.
Yeah. Okay, we will find a way to get you to answer my questions. Okay, thank you.
Yes,
thank you. Thank you, Dr. Cyrille, for a very interesting look into the future. Now we'll now introduce Professor James Wang. As I mentioned, he's known as the Steve Jobs of rotorcraft, and he's been involved in a lot of helicopters in Sikorsky, Black Hawks, and everything. Okay. Now today, he's going to tell us VTOL aircraft 10 to 20 years and how that is going to shape our traveling pattern. Okay, so Prof James, go ahead.
Hello, everyone. Hello, everybody. Lim Yeow, can you hear me?
Yes, we can hear you.
Okay. So now we hear a very nice speech from the Airbus talking about the large aircraft, how they're going to do hydrogen. So now I'm going to go diving a little bit deeper into specifically electric vertical takeoff aircraft. So we're going to go down in size. So we're going to talk electric and vertical takeoff only. And what will happen in the next 10 to 20 years. Okay, so as we can see, the world, the traffic has become worse and worse. So is there a way that we can go above the ground and fly into the air, sort of like a subway in the sky system? And also pollution, CO2 is going to be a future problem. Can we go solve all these problems in an urban environment in a purely electric manner? So we have always dreamed from the Hollywood, we've seen personal flying mobility. For now, finally, after 50, 60 years, that dream can become a reality now. So Hollywood is great. They come up with simple ideas 50 years ago, and now Hollywood has changed over a year or two to come up with even more luminous and different type of thinking now. So the dream is we could always take from home, fly to the office, between office and go to shopping, everything, have our personal air mobility. That is our dream for many years. So let's talk about eVTOL, which stands for electric vertical takeoff and landing. How did it all begun? Now let's turn the clock back to 1 decade ago, 2010. So 2010 to 2020, there was a great insurgence, a rising of research into the thinking of electric propulsion. So back in 2010, I had the ideas, why don't we make electric eVTOL aircraft? Because my job is basically for the last 30 years, I have been working in the helicopter industry as Sikorsky aircraft and also at Augusta Westland helicopters. So I came up with the idea, let's design an all-electric vertical takeoff machines. This was the aircraft I designed when I was at Augusta Westland back in 2010. And we flew it. And there are many benefits to this. For example, electric, the motor can get 90 to 95% efficiency continuously, while engines only have a thermal efficiency around 25%. You can even overpower, means put more current, get extra 30% power for a few minutes until the temperature is too high. You don't need a gearbox, transmission, drivetrain. The motor can be directly coupled to the propeller. So it's very easy to vary the RPM, few moving parts. There's only 2 ball bearings supporting the rotor shaft, very low noise, no polluting exhaust, low thermal signature, and you don't need oxygen for combustion. Therefore, it's altitude independent. Here on this chart, I'm showing on the vertical axis, I'm plotting the specific power. That means how much power, how much watts you can put in per kilogram of weight versus year. The blue dots represent many different jet engines, about 100 engines. We took an average. Over a year, we see the level is about 5,000 to 6,000 watts per kilogram. If you divided that by 746 watts, it gives you about 8 horsepower per kilogram. So for every 1 kilogram of mass, we can produce 5,000 to 6,000 kilowatt, 5 to 6 kilowatt, or 8 horsepower. Let's take a look at the green line, which is the piston engine. Relative low, only about 1,000 watts per kilogram. Diesel engine, even heavier. The red line represents electric motor. As we can see, it had quantum improvement over the last 40, 50 years. From 2020 to 2030, we can probably expect the specific power of the electric motor to even exceed turbine engine. So there's a future for electric flight. So finally, the secret project, the Project Zero that we built and designed, built, flown from 2010 to 2011, the company decided to unveil it, make it unsecret in the 2013 Paris Air Show. So this is actually a result shown by Lufthansa, the Innovation Hub. They did this analysis. So on the vertical axis, it shows a number of media reports on electric VTOL aircraft and urban air mobility. So from 2010 to 2013, there's almost no news on them. Very few people working on them. After we released it, showed it in 2013 Paris Air Show in the second quarter, immediately you can see there's a rise in the bar of number of media report, almost 4,000 media articles on electric propulsion. And that got a notice of many companies around the world, including Airbus, Boeing, and others. So now today, 2018, 19, 2020, we see a huge rise in the number of media electric VTOL and the urban air mobility. This shows there's a great interest. Let's take a look. 2015, Airbus started eVTOL aircraft. So they also realized this is going to be the big one. 2018, Bell Helicopter in the US also started launching their own program. 2019, Boeing also started. They started by first, they purchased the Aurora Flight Science, and then now they collaborate with Google and Porsche to work on their own version. So now all the big OEM just started in the last few years to get into eVTOL. So from 2010, For the Project Zero time, now we can see up to 2019, there have been over about 200 designs of these eVTOL aircraft. The number of growth in startups, OEM that are working on them has exponentially grown. 2015, even that time, there was only less than a handful, under 10 companies working on. Today, 2020, we can see over 300 groups working on electric VTOL aircraft. This is a great time for aerospace engineers again. We can dream and build aircraft, and it allows all the newly graduate engineers to find a place to work on them. And these are developing regions around the world. Majority are in the US, 48%, 42% are in Russia and Europe. Actually, majority of that is mostly in Europe. And Asia, we only have 10% currently. So I highly encourage everyone to get into this in Asia, because Asia is the future where we'll be utilizing. So right now at Nanyang Technology University, where I am teaching, and also I'm the director of the eVTOL Research Center, we are dedicating and developing our own eVTOL design right here in Singapore. This shows the trend of all the innovative new experimental rotorcraft and vertical takeoff aircraft in the last 100 years. When Igor Sikorsky invented the helicopter back in 1930, he was one of the few pioneers. As you can see, the number is very small. The vertical axis represents a quantity. From 1940 to 1970, during the World War II time in the Cold War, we see a rapid growth in innovation, experimental development of rotorcraft. Then there was a slowdown from 1970 to 2010. And then from 2010, when the electric started coming on board, now we see an exponential growth in the number of companies, startup, OEM working on electric aircraft. Every one of these lines represent one company, one design. Now let's talk about 2020 to 2030. So this is what something called the from Gartner Group, this is the hype curve. So with any innovation in the beginning, there's an innovation trigger. Could be mobile phone, internet, electric car. Then we see a rapid growth in the expectations of people. Until a few years later, they'll reach a peak, and then people start losing interest. There's a trough of disillusionment, and then was pick up again, and then the few companies surviving will be able to continue. So where are we currently right now in the eVTOL? We are right now are still around here on the rising stage. That's why there are 300 companies working on this. Then probably we can see up to 400 even. Eventually, 90% of these 400 companies, they will not survive. That is when it goes to the trough. And then what will come out is probably 20 companies that will come out and with good top 20 designs. So majority of startups will not survive. Because why? Not enough experienced eVTOL designers in the world, and not enough capital to support 300 teams worldwide. There's only a handful of helicopter and rotorcraft eVTOL design in the world, and not enough to sustain the 300. Even though today there are about $2 billion funding put into it, but it won't support 300. So the ecosystem eventually can support 15 to 20 eVTOL company and many supplier associate business. And Morgan Stanley have forecast this market will be at least US $1.5 trillion by 2040. So now let's go into a little more technical. We often hear the word energy density, specific energy. They're not the same. For eVTOL, the useful measurement for battery is specific energy. We want to improve the specific energy. So what is specific energy? Specific energy is the energy per unit mass of a fuel or battery. It's measured either in megajoule per kilogram or watt hour per kilogram. That's why it's called specific energy, specific mass. And of course, the higher the number, the better. Let's take a look at some of the specific energy number. Diesel fuel, quite good. That's 12,000 watt-hour per every kilogram. Burning coal, you'll get 7,500 watt-hour per kilogram. Even burning wood, you get 4,000 watt-hour per kilogram. Propane gas, excellent, 13,000 watt-hour per kilogram. Whereas lithium battery is like what we use in our iPhone, in our cameras. Lithium battery, only 200 watt-hour per kilogram. Extremely low compared to all the other energy sources. However, we have seen electric battery has gone great improvement over the last 60, 70 years. From in the vertical axis is the specific energy, the watt hour per kilogram. With the typical lead acid battery in your car, you only get 50 watt hour per kilogram. Now over the years, we have nickel cadmium, nickel metal hydride, seal lead acid, lithium polymer. Today, the Panasonic 18650 lithium cells using Tesla Model S, we can expect almost 250 watt hour per kilogram. But 250 is still pretty low compared to burning fossil fuel. What's the future? We can maybe expect up to 400 by 2025, 500 watt hour by 2030. So energy density. So before I talk about specific energy, now let me just, what is energy density? Energy density is the energy per unit of volume for fuel or battery. So it's measured as megajoule per meter cube, and the higher the better, the number. So how much energy we can put in the 1 meter box. So it's different than specific energy, how much energy per weight. So here is a trend showing the energy density over the years. So in the last decade, we can see we're rising from 2014, we have only about 100 watt hour per liter. And now we improved 2020 to about 400 watt hour per liter. It's a measured volume. And then in the future, we can expect for lithium battery to go up to about 750 by year 2035. It's almost double, but still not a quantum jump. In the last presentation, Airbus spoke about hydrogen. So now let's take a look on the vertical axis, energy density, how much energy per volume. Horizontal axis, we talk about specific energy, how much energy packed into per weight. Lithium battery is always on the bottom left. It's very low in energy density, very low in specific energy. It's not that great comparing to what? Natural gas, much higher specific energy, and butane gas, liquid natural gas, diesel fuel, they all have much higher energy density and specific energy. Where's hydrogen? Hydrogen is all the way on the far right. Hydrogen has very high specific energy. It means you can put in more energy per weight, but the volume is big, right? Because very low, I mean, take on a scale. Hydrogen gas, extremely low, that's not good. And then hydrogen gas, if we compress them to 700 bar, okay, a little more dense, you can put more energy density per liter. We can even compress more to make them the liquid hydrogen. Okay, now we get more energy density per liter, but still it's not that great. This was the problem that Airbus mentioned, that where are they going to fit all those hydrogen gas on the airplane? So that is a challenge still yet to be solved. That's why hydrogen is still not flying that airplane. Another problem for using hydrogen on smaller vehicle, like an eVTOL aircraft, the problem, how are you going to ship the hydrogen? Hydrogen is difficult to produce and very expensive. You have to produce it in a factory. How do we ship it to all the different charging stations across Singapore, across the city? So that's a big problem for hydrogen. Their cost, difficult to handle, difficult to ship. But for large commercial aircraft like what Airbus proposed, it may be possible because then we can have all the large airports have their own hydrogen manufacturing factory and fill up there. But for our own personal eVTOL, personal car, it's very difficult to have the hydrogen at every station. That's why we don't see hydrogen-powered fuel cell car yet. This one shows another different way of presenting what is a battery requirement in order for it to achieve eVTOL aircraft. On the vertical axis, again, is the specific energy, how much watt-hour per kilogram. On the horizontal axis, I'm introducing a new term called the specific power. What is the specific power? Specific power is the ability for the battery or the fuel or the hydrogen to give you the power you need. So it's measured in watts per kilogram. Today, the 2020 technology boundary for lithium battery is shown that by the red line. So what we want to do is push that red line further out to the top right to where the green star is. That's the minimum requirement. That means we would desire to have at least 500 watt-hour per kilogram of specific energy. We would like to have at least 2,000 watts per kilogram of specific power. That's the minimum we need in order to have at least half an hour of electric vertical takeoff flight. For the commercial aircraft that Airbus is describing, that will need to require to push that green star even much further to the right. Okay, so probably over 1,000 watt-hour per kilogram and beyond, actually 2,000 to 3,000, and also specific power requirement to at least 2,000 to 5,000 watts per kilogram. The one good thing about electric battery is the price is dropping. On the vertical axis, we see the price of being measured in dollar per kilowatt. The yellow line shows the battery price has dropped significantly over the last 20 years. Why? Because the blue line shows the demand for batteries around the world. Mostly this is driving by electric vehicle. They are the ones pushing for demand. Battery, lithium type, could be very dangerous. They can catch fire spontaneously. This is what happens when the lithium battery goes on fire. We have seen news that Tesla car, when they accident, it goes on fire and you couldn't put it out. So there still need to be a way we don't have yet, how to contain the lithium fire once it started. And the best, how do we prevent them from happening? Lithium is very volatile. So right now there's a global race around the world to certify eVTOL aircraft. Every country wants to be the first one. So back in 2017, United States or the FAA already started, modified their Part 23. 2018, the UK also started, then working on it. They granted a company in Bristol called Vertical Aerospace the flight test permission. And then 2019, China, SIAE, they also issued guidance on UAV, unmanned aircraft. 2019, EHang, a Chinese company, received the authorization from CAS to start testing. Now, you keep looking to the right, farther right, and farther right. 2024, Paris, they want to beat the rest of the world to be the first one to have an electric VTOL aircraft flying and working in Europe in order to demonstrate during the Olympic time. So the Europeans are working extremely hard also to compete against the rest of the world. Today, there are over 50 cities. They want to explore urban air mobility for carrying people and cargo. Los Angeles, Dallas, Melbourne, Dubai, Rio de Janeiro, even Singapore, we want to launch urban air mobility, electric vertical takeoff aircraft by 2025. In Paris, 2024. It's a global race. This is the curve. It shows what is going to likely happen. Back in 2010 to 2020, that's called the stage one. We saw a few stealth prototype development, like the Project Zero. We pioneered electric flight. And then stage two, 2020 to 2025, that's right now. There are many proof of concept electric eVTOL aircraft flying. The regulatory, like FAA, EASA, CAS, we're all engaged in figure how to certify them. 2025 to 2030, we can expect about 12 cities around the world to start operating urban air mobility, including Singapore. Singapore has a plan to offer sightseeing and tourist flight in Singapore around 2023 with the company Volocopter and also with Skyport. As shown in the top left picture, they already demonstrated in Singapore last October. 2030 to 2040, we can expect urban air mobility to expand to about 100 cities around the world. And 2040 and beyond, we'll see large-scale deployment of eVTOL and urban air mobility. So now let's take a look at 2030 to 2040, the future. In the future, this is a study done by Porsche Consulting Group. They predict Asia will be having 45% of all the usage of eVTOL and urban air mobility. Europe, 25%. America, only 30%. So right here in Asia, this is where most of the urban air mobility will be used. We will need millions of them, lots of them. The old-fashioned way of manufacturing helicopter in small quantity is not viable anymore. Because right now, these companies, they only measure about 200 helicopters per year. In the future, we must be able to manufacture them in robotic style, autonomously, just like producing cars. Make them cheaper, faster, quicker, and more of them. That is why huge future demand for eVTOL already got the automotive interested. Today, Toyota, Hyundai, Mercedes, Audi, Geely in Shanghai, even Google, Intel, and Airbus, Boeing, they all want the market of this electric vertical takeoff, urban air mobility. No one wants to be left behind like Kodak. So let's take a look, 2030, 2040, there'll be many hubs, vertiport per city. This is an aerial view of Los Angeles. And probably by 2030, we can see 20 vertical hubs putting around it. Each vertiport will look like this. And they will have a mega tower, allow simultaneously many eVTOL aircraft to come in and landing at the same time. It's almost like a sky bus system in the city. This probably won't happen until 2035 in this large scale. In the beginning, 2025, we'll probably see very small vertiport, just only allow 1 or 2 aircraft to take off, landing simultaneously. So 2035, what can we expect? This is the vision actually proposed by Uber. 1,000 landings per hour, 1,000 takeoff per hour. Each one carry 5 passengers, all autonomous, no pilot. That means every hour there are 10,000 passengers on only a 3-acre lot. That's a very, very high throughput. How can you achieve that? So this is one, so you will have one eVTOL coming on the left, come to the landing pad, they'll unload the passenger, just like a Disneyland ride, and then quickly they will load up the new passenger and then take off again. All this must be done within a 6-minute period, landing, unloading, loading to take off. During the 6 minutes, they also will give a quick zap, a quick charge of the battery. So this is my last slide. Let me explain how does this quick charge 6-minute scenario work. So let's take a look at the right. So basically for each mission, you'll be able to take off, hover for 1 minute, cruise for about 10 minutes to your next vertiport. For example, it could be from Jurong East in Singapore all the way to Changi Airport. That's only a less than 10-minute cruise. You'll land in 1 minute, and then once you land, and then they will plug, charge the battery for 6 minutes and unplug. So that is how it works. So Singapore, maybe we can set up 10 different locations at Changi Airport, at Jurong, at Woodland, at the Sentosa Island. So that is how these urban air mobility work. Now let's switch attention to the left side. On the left side, the vertical axis shows the battery charge capacity. On the horizontal axis shows the amount, duration, minutes we can expect from the battery. So start of the morning, the aircraft is fully charged, you have 100%. So this eVTOL, it will fly to the first mission, like the first subway stop. It go by doing this 10-minute flight, in the first mission, you'll burn up about 25% of the electric battery. And during the 6th minute, you'll do a quick zap, charge up the battery again, you bring it back up to 90%. And then you go to this next stop, another 10-minute flight, you'll drive down another 25%, back to about, now down to about 65% of the battery juice. And now you do a quick charge upon the landing, and then you repeat. So you can basically do about 10 of these missions hopping before the battery reaches about 40% of its capacity. At 40%, we will need to either stop the eVTOL aircraft to swap out the battery for a fully charged one, or let it rest for 1 hour and charge fully in 1 hour and continue this 10 hopping mission again. And why are we stopping about 40%? Because we need to have a reserve. You don't want to run the battery continually till dry, right? So you need a reserve of at least 15-minute cruising. And also you should never run your lithium battery, even on your cell phone, below 10%. It's not good for the battery. So this is how electric eVTOL aircraft, it can definitely work in the next decade. So eVTOL is likely to happen between 2025 and 2030. And by 2030 and beyond, we can see complete autonomous eVTOL flight. And the range, we can expect today at 2020 to be about only 50 kilometers. And we will start seeing improvement by 2025, go to 100 kilometers. Most of the benefit will come from optimizing the aircraft structure, reducing the weight, and making more efficient design. From 2025 to 2040, we can expect a lot of improvement in range due to the specific energy improvement in the battery. So on the bottom, I'm showing that specific energy level today at the pack level is about 160 watt-hour per kilogram. By 2025, we can expect to go about 200. Then we can keep expecting to go up to about 500 watt-hour per kilogram by 2040. That is where the major improvement. Now, 500 kilometer range is pretty good. We can pretty much fly from here to Singapore. So this could be the future. We look up the sky, we will see lots of eVTOL flying. Thank you. And my email's down there. If anyone want to contact me with question, is james.wang@ntu.edu.sg. This is what my center we're doing now. We actually designing a complete eVTOL in Singapore. By 2027, we would like to have it certified and flying around the world. Thank you.
Thank you, James. Great. I think we are all very enthusiastic, noticing that Asia is going to be the leader.
Yes.
All these activities, and our aerospace engineer will have a lot of opportunities to play with this long before the other people get in.
And there'll be lots of jobs in Singapore.
A lot of jobs, yes.
For aerospace engineer.
Excellent. So, but just a quick question, James. You have so many technology front, right? You have the fuel density, what I call fuel density, as well as power density.
Yes.
So many fronts to hit, batteries, like mobilities and everything, regulations. Which one do you think is likely to cause a bigger problem?
Right now, I said all the technology we can manage. The biggest problem is that right now we need to get the regulatory, which is the government, to actually work closer and faster with the dreamer, the engineer, the company, the industry, to come up with a way. How can we manage hundreds and thousands of these flying in the sky? How can we make them safe? That, I think, is the biggest challenge, right? Because, I mean, you and I, we look up the sky, and then from a home, another aircraft flying over, another one. Just like Amazon want to deliver, I mean, your new product, and then Grab want to deliver your new pizza, everything by a little drone, right? We don't want one of these to fall down, hit us, and also don't want them to collide in the sky. So I think the regulation is the one that needs to...
It's a challenge, right? Yeah. Right. What about talents? How will Singapore get enough talents to take advantage of this industry that's coming up?
Well, that is why at NTU, I created a center now. I'm teaching new engineers into this area. So we are graduating about 100 aerospace engineers a year. So in terms of people, that's not an issue because before they don't have a design job, they will mostly go to MRO and other service industry. Now they will have a chance for Singaporean engineers to electrical engineer, computer science engineer, materials engineer, aerospace, to apply their creativeness, innovativeness to really put in design something rather than just in doing the surface industry. And we graduate hundreds of engineers, there'll be plenty of job for them in the next 1 or 2 decades.
Thank you, James. I understand you have to leave for another assignment. Those of you who have any question, write to James or you can write to us, and then we'll find other ways to give you the answer. Okay.
Thank you very much.
Thank you very much. We can continue this discussion for another half an hour. For those who want to stay, James, you can take your leave. I understand you have to attend for another event. Okay. Okay. I think we have two very, very interesting and very far future look into more the fundamentals of how the aviation industry, the aerospace industry, is going to evolve 20 to 30 years from now. And I really appreciate Dr. Cyrille Schwob and James for coming to this webinar. And I find it's very exciting for us to have, instead of looking at the gloom of COVID, we are looking 10, 20 years ahead. Okay. Anybody here has any question or anything you want to ask, or what SIAE can do to achieve the dreams, and any recent questions you want to bring up, I'll be happy to talk about it. Yeah. Nobody? How would they respond?
They can type.
Okay. So we are trying to manage the Zoom. This is the Zoom, right?
Yeah, with because we're in a webinar mode, so they can use the chat to type the questions.
What you're hearing?
I can actually allow them to. Oh, there's allow them to
talk.
To talk. Yeah.
What you're hearing is Daryl, who is our technology expert in handling this.
Okay, Kenneth, maybe.
Yes, go ahead, Kenneth.
Kenneth, see.
Kenneth, please go ahead.
Sorry, can you hear me?
Yes,
yes, we can hear you now.
Oh, okay, because it wasn't announced previously how we're going to field the question. So I was typing halfway, then I was allowed to speak. Just an understanding about how these two experts are going forward with their presentations. Interesting that Cyrille, right, is his name.
Cyrille Schwob, yes.
Cyrille Schwob. He has presented a case where how Airbus is leveraging on hydrogen fuel technology to design airplanes for the purpose of long-range travel. It means to say that they have planes that is zero emission and can go up to maybe 2,000 kilometer range, that kind of plane for long-range travel. And then, of course, Professor James Wang, which is on eVTOL technology, which is leveraging on travel for, aircraft that can go 200, maybe 300, maybe up to 500 kilometers range. So two different directions, I can understand. What is interesting I wanted to ask about Cyrille is there actually a working electric motor turbo fan or turbojet engine for that kind of design, which is rather huge and really difficult to solve. But of course, from James Wang, we have seen the tremendous research has done for electric motors powering the eVTOL, which is technically feasible, already concept proven. Just wondering if there is such a thing. Yeah, that's my question.
Anybody in the audience has an answer? from what I gather from James and Cyrille, like they are looking, as Kenneth had mentioned, they are looking at totally different area. James is looking at urban mobile vehicle, right? UAM, okay? Whereas Cyrille is looking at much more long range, and the technology are actually quite different. So if you are looking at whether there's a turbofan, electric turbofan running, right? There is actually one, right? There's a Chinese, I think there's a Chinese company, Yihan, right? They actually produced an aircraft using purely electric. The issue here is the range. It won't be, the range is very limited. And I think it's set about 4 people. It's a very small payload, okay? So the problem here, you can see, 2 different areas. Here, James tell you all the motor has the highest, what I call power density. But the issue here is the fuel capacity. You know what I mean? The hydrogen itself,
that's right.
or battery itself. So there are 2 different technologies developing very fast, which is why I think you saw what Dr. Cyrille Schwob was saying. We look into other industry, right, for guidance. And the electric car industry will give you the link where we're heading in terms of battery energy. See, whereas I think the motor power energy will have to come from the aerospace industry, because we are expert in making things lighter, you see.
Yeah, correct.
I mean, I think it's a very interesting discussion. We could actually create a few more webinars with experts in this area. Take note of it, Darryl. Yeah. Thanks very much for bringing
really
up.
correct. It was very fun and very enjoyable.
Yes.
Yeah.
Very interesting. Yeah.
Okay. Thanks.
Anybody else? There's another question there.
So I think he typed.
Oh, there's Kenneth, right? Okay.
No, Johan, sorry.
Johan, go ahead.
Okay, he typed a question, so
you can talk better.
Okay, so I disable Kenneth and Johan. Allowed to talk.
Johan, go ahead.
You have to unmute. Okay. Oh, maybe he typed the question and he stepped away. So why don't you try to?
Okay, Johan, I'm not sure whether you are hearing us.
We have a question from Johan of Swatchlog.
Okay, Swatchlog said, okay, the panelists mentioned a lot about energy source, be it battery or hydrogen for planes of the future that will be affecting plane design. How do you see that impacting the curriculum of aerospace engineers? How do you think existing technicians in aviation industry can prepare? Very good question. In fact, this is already preempted by many institutions. For example, at the last industry advisory panel of NTU, which I sat on, we discussed a lot about electrification of aeroplanes. So well, a lot of people were talking about electrification in terms of propulsion, right? Already happening is that the aircraft itself is highly electrified. So it's not just the propulsion. Everything on the aircraft has. So the curriculum, my recommendation as the industrial advisory panel is to have more electric courses in the mechanical in the aerospace program. Okay. See, right now we have a lot of courses that are actually taught by electrical EEE department. Okay, the aerospace industry now has to, aerospace department now has to boost up the teaching of, and that goes down all the way to the polytechnic and to schools to push up more on electrical engineering or electrical science. Yeah. Thanks, Johan, for bringing me. I think it's a very important thing. that we should prepare ourselves for more electric in all vehicles.
William.
William, go ahead.
William, you can unmute.
Okay, that's William from SIAE. Okay, I hear Professor James mention about career opportunity and that NTU is having about 100 graduates a year.
Yes.
And there's a lot of opportunity for this career in the VTOL industry. But look, and you're talking even to a time frame of say 5 years from now. But looking at the scope, the company that is available in Singapore, I don't see actually any company or organization right now in Singapore that has actually started in this direction or in this kind of project. So I really don't see how within say 5 years you can have in a growing or mature industry that can actually absorb this 100 graduates every year. I think it's a bit ambitious.
Okay. You're right. William is right. I taught in aerospace courses, and every year we have about 100 students. Okay. Interesting, I had an observation. I teach this course called Aircraft Navigation and Flight Computers. Previously, my class used to have about 30 to 40 students. But this semester, I got 131. So it looks like the students are already responding to more electric in their course. But this is a kind of an elective course, you see. Yeah. So what James was looking at here is R&D. In other words, we are looking for companies to invest in eVTOL now. Okay, which means, of course, that they're not going to take all the 100 graduates. Okay, what James also saying that many of the current 100 aerospace engineers move out into MROs and finance, leasing companies, and all these things because there were insufficient R&D aerospace in Singapore for that. But this represents what I call a jump, a leapfrog into a new area of technology, which is not the traditional. You see, the traditional aerospace research R&D were already in the matured aerospace companies like Europe and America. Okay, so you can see that this leapfrogs a new technology, and he predicted that Asia will probably be the biggest market, and so it is prudent that companies in Singapore or in Asia invest in this area, and that will absorb more of our engineers. Doesn't mean take all the 100. There's a slow migration of more of our aerospace engineers into the R&D part of aerospace. Yeah, William, you're right. It won't happen in 5 years.
Maybe I can comment on it.
Yeah.
So currently, I think the most famous company that is based in Singapore, they are doing trial demo flights. It's called Volocopter. Of course,
yes.
as James mentioned, the biggest challenge now is regulation and how do you regulate, and ensure safety. So I think if it is successfully rolled out in Singapore, then I'm sure Volocopter will try to go out to Southeast Asia and everything. So
it's already there. That means there's a big company already anchoring this.
So Singapore could be the hub for them to operate and manage out of the region. So again, we are not limited to working in Singapore only.
Correct.
Yeah.
Correct, yeah. So Volocopter and in fact CAS and Airbus are involved in this urban air mobility project. So which is why CAS was involved right from the start to make sure that the regulation won't be the obstacle to the speed of progress.
Yeah, Yeow Khee.
Go ahead.
So Yeow Khee, I think you are right. I think the focus now would actually be very important for the government and EDB to actually focus on organization that specialize in R&D in this kind of technology to actually encourage them to come to Singapore. I give you an example of biomedical.
Biomedical.
That the EDB encouraged probably about 10 years ago, 10, 15 years ago, and it took that kind of number of time. And then that's why now,
it take a long time.
Now with the COVID thing, you notice we are actually also in the forefront. We have developing vaccine and things like that, and we are among the world leader. Okay, so I think the same kind of focus needs to be given to this industry so that in maybe not 5, 10, 15 years time, we will be also in the forefront of this industry. So I think that push needs to be given to EDB and to the government to actually encourage this kind of R&D in Singapore.
Yes, there's a question from somebody. I just read to you. James mentioned that there will be lots of opportunity for aero engineer. As a recent graduate, one foreseeable problem is over the last 2 batches of graduates due to COVID, many aerospace graduates had no choice but to turn to other industry to work. Okay, how can we come back into the aerospace industry, especially if companies might see our past work experience and not offer an interview because we were in unrelated industry for the last 2.5 years? Very good questions. I think my obvious answer here is to keep in touch with the industry. And this is where Singapore Institute of Aerospace Engineers is here for, you see. And that's why we organize this. Keep in touch with the industry. You may not be working directly, right? But you can still get involved, for example, in this webinar. Okay, keep in touch with industry and update yourself, right? For example, what I call journals, keep up and all these things. And this is where SIAE comes in to do this. And this is exactly what we wanted. Thanks for the question, because it does prompt us to pay some attention to your group of people. Yeah, I'm sure our EXCO member agree to put more attention to that. Okay, any other question? Back to the part we're discussing about this migration. It doesn't happen immediately. And I happen to have a little bit more information about what William just mentioned. It is actually the molecular biology technology, which interestingly was started in Singapore by Goh Keng Swee many years ago, when nobody thought that this is going to be useful. And we have even a Nobel Prize, Nobel Prize winner working in Singapore on the Molecular Biology Institute of Molecular Biology. And it's a world-class Institute of Molecular Biology, which very few people know about it. Okay, his name is what called Sydney Shannon somewhere. I think he passed away about 2 years ago. Okay, in Singapore, he actually worked in Singapore. Okay, and when COVID comes in, you find that Singapore was actually on the forefront of many of this technology to come out with a cure. Okay, thanks William for bringing it up. I think the aerospace industry need to kick off early. Okay, and I think Darryl just mentioned Volocraft is already in here. Yeah. Any other questions from the floor? We still got a few more minutes to get away. Sometime no more. Okay, okay.
So Kenneth asks,
are we able to replay this recorded session or recap on some of the topics on the
website? Okay,
this session is recorded and you'll be posted on our website.
Yeah.
Do we need to have special for members only or anybody?
So far, I think we can open it.
Okay, so you open to the public. Darryl just mentioned to me. Yes, Kenneth, answer is yes.
And then I think Airbus need to get clearance to share the document. Yeah.
Okay.
The PDF itself.
Yeah.
But I think it should be okay, he said. Yeah. So we'll check our website.
Okay, that answers your question, Kenneth. Anybody else? Any questions? If not, I think I'll just close this seminar, this webinar. Thank you very much for your attention and participation, especially active participation.
We can give them a teaser maybe in 2 months' time.
Yeah, I think we will try and organize more of these. every 2 months we'll try and do one.
Yeah.
Okay. And for the young student who just graduated, keep in touch. And then you'll see that we have more exciting things. I feel very energized after listening to these two guys.
So if they have topics also,
if you have interesting topic, just put on our website. I think we'll create a forum for us to discuss on all this. Okay, with all this, I just need to thank everybody, especially I want to thank Daryl for setting this up and our two speakers, James and Dr. Cyrille Schwob for kind of willing to come around. And despite the fact that they have another engagement, which is why they have to rush off. My apologies to all of you, but we can reach that. Okay, thank you very much. We will close this webinar.